There are some equations that bear some similarity to quadratic equations, even though they are not exactly quadratic or second-degree equations. Some of the features that make them similar to certain types of quadratics is that they are often three terms or trinomials. So we see here x to the fourth term and then an x to the second term and then a constant or plain number term. Down here we also see terms with bunches of stuff. So in the first term, the bunch of stuff is squared. In the second term, the bunch is not squared, but it has a coefficient in front of it. And the third term does not have that bunch, and so it's constant. So what we are seeing is that the middle term contains a certain element that is squared in the first term. And in this third example here, the middle term contains this square root of x, but the first term is the square of that square root, which is just x to the first power. And so whenever we have the first term with something squared, the second term with that variable or that expression not squared, and the third term a constant, we can then treat it as if it were quadratic, even though it's not a second-degree equation. Sometimes we will use a construction that we'll call u, and we will let u be the variable part that's in the second term, in this case x squared, because the first term is the square of that value. So what we're seeing is that to get x to the fourth, we will make that u squared. And then finishing out the equation, we've got minus 19x squared becomes minus 19u plus 48 is equal to 0. And again, u squared, when we square that u, x squared squared represents our x to the fourth. And now you can see this is a second degree or quadratic trinomial, and we can factor this. Factors of 48, we're looking for a sum of 19 in the middle, so we get 16 times 3. And we get the factors that u minus 16 times u minus 3 is equal to 0. We can solve for that and say that u then is equal to either positive 16 or positive 3. And wow, that feels like we're done. But unfortunately, we have not yet solved for x. So we need to go back and make use of the fact that u is equal to x squared. So where we had put u is equal to 16, we then need to say that x squared is equal to positive 16. And that's going to give us two results. That's going to give us that either x is equal to positive 4 or negative 4. Next, we'll take a look at the second solution of u, which is equal to 3, and realize that u, again, is equal to x squared. So we're going to say that x squared is equal to a positive 3, and when we take the square root of that, we end up with, again, two solutions. We get that x is equal to either the positive or the negative square root of 3. So when we write out our solution set, we have four solutions. We have negative 4, we have negative square root of 3, and we also have positive square root of 3 and positive 4. For our next example, we're again going to use u to represent some cluster, and in this case the parentheses make it fairly straightforward to use that as the value of u, so we're going to let u equal to x squared plus 2. And you can see in this equation that then letting x squared plus 2 be the parentheses, we've got u squared minus 6u plus 8 is equal to 0. So this is a quadratic equation that's fairly easily factored. And we get u minus 2 times u minus 4 is equal to 0. And we can solve for u. We end up with u is equal to positive 2 or positive 4. And just like before, we'll remember to substitute our expression using x for u. So choosing our solution of u is equal to 2, we set that equal to x squared plus 2, and solving for x squared, we'll subtract 2 from both sides, and we get that 0 is equal to x squared, or that x is just equal to 0. From our second solution, that u is equal to 4, we'll substitute in x squared plus 2 for u. We isolate x squared by subtracting 2 from both sides, and we get 2 is equal to x squared. And finally, solving for x, we'll take the positive and negative square root of both sides, so we get x is equal to plus or minus square root of 2. When we look at the solution set, we can see that x is equal to a negative square root 2, but also 0 or a positive square root 2. And I'd like to take a moment to look at these solutions and the degree of the equations. So in our first example, we had a fourth degree equation, and you can see that we had 4 solutions here. In our second equation, we had x squared plus 2 raised to the x squared. So this also is a fourth degree equation, but the first solution that we got, x equals 0, turned out to be a double solution. We had 2 factors of x which multiplied to produce that, and so we end up with 3 unique solutions. Let's move on to another example. And this time our equation, x minus 2 square root of x minus 15 equals 0, appears to be a first degree equation. However, it's got this radical term in the middle. And this time we are going to think of x as being the square of the variable part here, this root x. So we will let u equal square root of x, and we can rewrite the equation. So x is actually equal to u squared minus 2 times the square root of x, so that's 2u minus 15 is equal to 0. This can be easily factored, and so we get u minus 5 times u plus 3 is equal to 0. And from this we get the solutions that u is either equal to a positive 5 or a negative 3. As before, we'll go back and set our expression with x equal to u. So we get square root of x is equal to a positive 5, and solving for x, then we get that x is equal to 5 squared, which is equal to 25. For our second solution, we let square root of x equal to negative 3, and squaring both sides, we then get that x is equal to 9. We now need to go back and check these solutions because the original equation was a radical equation, and in particular, this solution where the square root of x is set equal to negative 3, I'm imagining might give me some potential problems because squaring both sides and squaring a negative number can introduce a false or extraneous solution. But let's go back and check. So we'll first test the solution, x is equal to 25, and I plug it in the original equation, x, which is 25, minus 2 times the square root of x, so that's 2 times the square root of 25. And we're going to ask ourselves, when we subtract off 15, is that equal to 0? And we can see here 25 minus square root 25 is 5, so 2 times that is minus 10, and minus 15, that does give us a true equation. This is equal to 0. So we feel good about this solution. Next, we're going to check the solution. X is equal to 9. So plugging into the equation, we get 9 minus 2 times square root of 9, which is 3, and then minus 15. And we're going to ask, is that equal to 0? And here you can see negative 6 and negative 15 gives us a negative 21, and that is not a true equation. And so this is a false or extraneous solution. So the only true solution is that x is equal to a positive 25. The last example we'll do involves negative exponents, but as before, the variable part for the middle term we can assign to the variable u, so we can let u equal x to the minus 1, and we are seeing that x to the negative 2 is actually the square of this. If we were to square x to the negative 1, we multiply the powers and get negative 2. So this equation can be rewritten, and we get x squared becomes u squared plus 3 times u plus 2 equals 0. Just like before, we can factor this equation, and we get the factors u plus 2 times u plus 1 is equal to 0. And from that we can get the solutions that u is equal to either -2 or -1. When we go back and substitute, letting u equal x to the -1 power, we get x to the -1 is equal to a -2. And remember, a negative exponent means that this is going to be a fraction. And so this is actually equal to 1 divided by x to the first power. And if we solve for x, you can think of this as cross multiplying, but we get -2 times x is equal to 1 times 1. And finally, when we isolate the x, we divide by a -2, and we get that x is equal to -1/2. So that's our first solution. Our second solution is similar. We get that x to the -1 is equal to -1. And setting that equal to 1 over x, we get 1 over x is equal to -1. And taking the reciprocal of that, we get that positive x is still equal to -1. So these are our two solutions. X is equal to either a -1 or a -1/2. And because this is a reciprocal equation, we should check for bad points. This 1 over x means that we should not be letting x equal to 0. But our solutions do not overlap with the bad point, and so these are two good solutions. The last comment that I'd like to make is that there are some students who are able to solve this type of equation without explicitly using the letter u. What they see is that x to the -2 is a square of x to the -1, and they realize that this is a trinomial which is factorable into two binomials. So setting up our binomials, realizing that the variable on the front should be x to the -1, we can write that in. And now when we look at the coefficients, +2 for the last term and then +3 for the middle term, we can see that the factors of 2, which add up to 3, are going to be +2 and +1. And then they are able to solve each of these factors. X to the -1 then becomes equal to a -2 or a -1. And taking this reciprocal, we end up with the same solutions as before, that x is either equal to -1/2 or -1. If you are able to do this without explicitly writing u, you can see that it's going to save you a little bit of work, and so I'd say go for it if it's practical. But if you're struggling and you really do need to use the u, that is a tool that's at your disposal, and feel free to use it as well.